Okay, the purpose of this presentation is to talk about heating curves. And a heating curve has to do with basically the physical properties of some kind of a substance. It could be a substance like a metal, like aluminum or iron, or we could be talking about an ionic compound like sodium chloride or magnesium sulfate, or we could be talking about something molecular like water or alcohol. And basically the idea is that if we have if we have a substance that's in its solid form, so I'm going to draw a picture here. This is a beaker, and in the beaker we're going to have some kind of a solid substance to start with. All right, and we're going to take and put that substance on a heating source. So on a really simple level, this could be your stove, for example, although you have to sort of like go with the program here, because if this was a piece of iron, for example, you're not going to be able to melt this and make it boil on a stove. But the point is that we're going to take this material, we're going to put it on a heat source, and we're going to heat it up using a constant rate. And then we're simply going to measure its temperature as a function of time. All right, and then we're going to take and we're going to plot that data on a graph and just look at what the shape is and talk about what it means. So we'll have time on the horizontal axis going this way, and then over here on the vertical axis we'll have the temperature, and I'm going to use degrees centigrade, although the temperature could be measured in science. It's either going to be degrees centigrade or it'll be Kelvin. All right, and for any substance, what we're going to see as we begin to heat this is that, and this is common sense, is that the temperature is going to rise. And the temperature is going to rise up to the point where the material begins to melt. And then you're going to see something remarkable, because the temperature is going to stop going up. And it's going to stay fixed for a while. It's going to stay fixed until the solid that we're heating completely melts. And once the material has melted and become a liquid, then we're going to see the temperature begin to rise again. And the temperature is going to rise, and it'll rise for a while, up to another point where you would see, if you continued to measure the temperature, that it had flattened out again. And the temperature is going to stay flat until the liquid has been completely converted into a gas. And then you would see that temperature rise yet again. And we end up with a curve that looks like this. And in the curve you can see that there's 3 regions where the temperature is changing, and you can see there are 2 regions where the temperature is not changing. So let's go through and label the parts. So in this section of the graph here, this is where we started our experiment, and the material is solid. All right, this section here is where the solid's being converted to the liquid. So this would be what we call your melting point, which is also called freezing point. The 2 terms mean the same thing. They correlate, let me put it this way, they correlate with the same point on this heating curve. This section in here is the liquid. This section in here is the boiling point. Boiling point of the liquid, whatever it is. And then this is the gas, this section. Now, what I'm going to do first is talk about the sections where the temperature is actually changing. All right, in these areas, if we are more specific about the temperature. So we call this delta T, meaning the change in temperature. In these regions, the change in temperature is not zero. The temperature is going up. Remember that temperature is a reflection. I think I'm going to write that down here. Temperature is a measure of molecular motion. Molecular motion, that's what it is. It's a measure of molecular motion. So in these regions where the temperature is changing, what I want you to try and do is think about what's happening in there, because going back over here to our diagram, remember that all the way across this graph, we're heating this substance, and the heating is being done at a constant rate. So we're pumping energy into substance at a constant rate. At a constant rate. So nowhere in this experiment, there's no place in this experiment where we've ever changed the heating rate. So even in these points where the temperature is not changing, we're still pumping energy into the substance at a constant rate. So coming back to the sections where the temperature is changing, what does that mean exactly? All right, we're pumping energy into the substance across these regions where the temperature is changing. The temperature change is not zero, so what's going on with the energy here? All right, so temperature is a measure of molecular motion. So in the regions where the temperatures are changing, the kinetic energy of the substance is increasing. So kinetic energy is increasing. So all the energy that's being used in these sections where the temperature is changing is going into speeding molecules up. They're tumbling faster, they're vibrating faster, their molecular motion is increasing. Molecular motion is increasing. Molecular motion is going up. All right. Now, what's going on in these regions where we're actually changing the phase of the substance? So at the melting point and the boiling point, this is what's called a phase change. All right, and in a phase change, it's important for the student to realize that you have the coexistence of two or more phases at the same time. So when you see that pot of water boiling on your stove just before you go to throw the pasta in there, you actually are witnessing the coexistence of the gas and the liquid at the same time. So looking here at the melting point, you have the coexistence of the solid and the liquid at the same time. And at the boiling point, you have the coexistence of the liquid and the gas at exactly the same time. All right, so at the melting point, the energy that's being used to do the melting is called the delta H of fusion. And at the boiling point, the energy that's being used to convert the liquid into the gas is called the delta H of vaporization. Now, what you have going on in here, and I want you to think about this, is that in contrast to these areas where the temperature is changing, the question is, where is all the energy going that's being used in these places where the temperature is not changing? Because remember that we have this substance sitting on a heat source, and the heat source is pumping energy into this substance at a constant rate. We have not turned off the stove here. The stove is on and we're pumping energy into this. So what is the energy being used for if it's not being used to increase molecular motion? All right. So what's going on here is that we're breaking bonds. All right, we're breaking bonds. That's where the energy is going. In the case of going from the solid to the liquid, we're breaking one or two bonds between either the atoms or the ions or the molecules. And in the case of the boiling point, we're breaking all of the bonds that exist between the particles. If you think about this, going from a liquid to a gas. In the gas, the particles are not connected at all. The particles are completely separated from one another, completely separated. So we've had to break every single bond that existed between the particles. Now, to put some perspective on this, if our substance was aluminum, the boiling point, or excuse me, the melting point down here is about 660 degrees centigrade if this was aluminum, and we would be breaking, in this case, metallic bonds to go from the solid to the liquid. If this was sodium chloride, the melting point is 801 degrees centigrade, and we would be breaking ionic bonds. If the substance was water, then the melting point would be 0 degrees centigrade, and we would be breaking molecular bonds. In the case of the boiling point, aluminum is around 2519 degrees. It's way up there because we're having to break metallic bonds for that one. For sodium chloride, the boiling point is around 1413 degrees, all right, because we're having to break, again, we're breaking ionic bonds, and metallic bonds for the aluminum, ionic bonds for the sodium chloride are way stronger than molecular bonds, because if you look at water, its boiling point is 100. Significantly lower than these others. So in finishing, I can draw an arrow like this to represent bond strength. All right, bond strength, where metallic bonds are essentially pretty similar to ionic bonds. They have similar kinds of strengths. You can see that here comparing the melting point of sodium chloride with the melting point of aluminum. But in the case of the molecular bonds, they're far weaker by comparison to metallic bonds or ionic bonds, because look how low this melting point is by comparison to aluminum and sodium chloride.